Good afternoon, ladies and gentlemen. Welcome to today's technical seminar, jointly organized by the Hong Kong Polytechnic University and HKIU Civil Division. Today's technical seminar topic is Inverted Pavement, Paving the Way for a Sustainable and Decarbonizing Hong Kong. We are very glad to have Dr. Jiang from the PolyU to share with us. Dr. Jiang obtained his Doctor of Philosophy degree in Civil Engineering, Pavement Engineering at the University of Tennessee, Knoxville, the United States, and a Doctor of Engineering degree in Civil Engineering, Geotechnical and Underground Engineering at Tongji University, Shanghai. Dr. Jiang's research interests revolve around geotechnical transportation engineering, with a special focus on the development of resilient infrastructure such as pavements and tunnels. In addition, he is passionate about exploring cleaner construction materials to foster sustainability in this industry. Without further ado, may I now invite Dr. Jiang to share with us. Dr. Jiang, please.
Okay, so you can see my slides, right?
Yes.
Okay, so good afternoon, everyone. My name is Jiang Xi from Shanghai, China. So today is my great honor to join the PolyU CE webinar series 2024 to 25 and organized by HKIE. So firstly, I will give a very brief introduction of our department, Department of Civil and Environmental Engineering at PolyU. So we have very good global recognition. We have 26 CE scholars ranked world top 2% scientists, which is released by Stanford University. And we have very good programs, such as we have best major in civil and structural engineering number 14 by QS World University Ranking System, and number 2 in civil engineering, number 2 in transportation science and technology, and number 22 in environmental science and engineering by Shanghai Ranking System. And we also have very outstanding faculty. We have 1 member of Chinese Academy of Sciences, 7 Changjiang scholars by the Chinese Ministry of Education, and 1 fellow of Australian Academy of Engineering and Technology, and 1 fellow of Royal Academy of Engineering in the UK. And we also have very good achievements in projects such as the theme-based research scheme from Professor Ni, Professor Li Xiangdong, Professor Teng Jingguang, and Professor Wang Tao. And we also obtained many special funds such as the GTF and the Lentil Conversation Fund, and the RGC Collaborative Research Fund, and Impact Fund. And our academic programs are also very good, such as undergraduate program. We have bachelor engineering degree in civil engineering, in environmental engineering and sustainable development. We also have the taught and the research postgraduate programs, Master of Science in Civil Engineering and Master of Science in Environmental Management and Engineering. And for the research postgraduate program, we have MPhil and also the PhD. And our alumni are also outstanding in both academia and also the industry. And we have 30 laboratories and 2 workshops, including the mechanical and the electronic. And also we have the 1 research center in Shenzhen. Here are the names of our laboratories, workshops, and research center. And if you guys want to have more latest news about our departments, we can, first of all, we can log in our department website. to check the latest news and to scan the QR code to check our CE newsletter. And also we have social media channels such as Facebook, Instagram, YouTube, WeChat, and all the social media platforms. Okay, let's go back to my presentation. Okay, so today the topic of my presentation is inverted pavement, paving the way for sustainable and decarbonizing Hong Kong. So I'm the research assistant professor at PolyU and collaborated with Professor Len Zhen. Okay, so this topic is based on based on my research in the United States. So based on the ASC, American Society of Civil Engineering Engineers Infrastructure Report Card in 2021. So due to the distress of the pavements in the states, such as the cracking, patching, or pit holes, surface deformation, and surface defects, the governments need to pay $400 billion to repair the existing roads. So under such a circumstance, we need to have the new payment structure, which can both save the materials and offer the good properties of the pavements. So here today, I would like to introduce one novel or unconventional pavement structure. Its name is inverted pavement. So we consider the inverted pavement as a good alternative to our conventional flexible asphalt pavement. So actually, inverted pavement is a kind of a flexible pavement structure where an unbound aggregate-based UAB is placed or sandwiched between a cement treaty-based CTB and the thin asphalt concrete surface layer. So here I give you a figure. So the surface layer is asphalt concrete layer, and the interlayer is unbound aggregate layer, and above the subgrade soil, we have the cement treaty base. So this structure looks like a sandwich. So many scholars give such a pavement structure the name sandwich pavement also. So here I give a comparison study between the conventional pavement in Hong Kong and the inverted pavement structure. As you can see between the two figures, there are several differences between the two pavement structures. One is the sequence of the pavement layer. In the conventional pavement in Hong Kong, we have the asphalt layer, unbound aggregate layer, and subgrade soil layer, just 3 layers. And also the modulus from the top to the bottom is decreasing with the depth of the pavement. However, in the inverted pavement, first of all, we have 4 layers. The surface is also the asphalt layer. Below the asphalt is the unbound aggregate-based layer and cement treaty-based layer and subgrade soil. So as you can see, the lowest modulus layer of the unbound aggregate base is inserted between the asphalt layer and the cement treaty-based layer, who have much higher modulus. So research gaps. So why do we investigate the inverted pavement? So the first gap is that the limited comprehensive investigation correlating the failed performance with the structural capacity of inverted pavements. We need to conduct experiments in the in-service inverted pavement, and we have to design a comprehensive framework of the test. The second one is that limited comparison study between the inverted and conventional pavements with the same environment conditions, such as the traffic loads and the same temperature, something like this. And the third research gap is the limited simulation work to investigate the stress-dependent property of the unbound aggregate materials. Inverted pavement collaborated with the field data. The first one is for the reinforcement of the inverted pavement through the geosynthetics. So here is the outline of the whole research project. So the objective is to give a comprehensive investigation on the inverted pavement and advance the understanding of the inverted pavement system with a combination of laboratory testing, field testing, and evaluation, and numerical analysis and simulation on both the inverted and conventional pavements. So we need to conduct field and full-scale investigation, and we also need to do the numerical simulations to verify our test results. So here are the research contents. We have 5 steps. So the first one, we have to do the preliminary numerical simulations, focusing on the stress-dependent stiffness property of the unbound aggregate. So many years ago, we have the very classical K theta model to predict the stiffening characteristics of the UAV unbound aggregate base. Since we all know that the aggregates are kind of under the repeated loading, the aggregates will become denser, and it will have higher density and stronger interlocking, and then it will have higher stiffness. Due to such a special property, so we have to conduct the simulation works to simulate the stress-dependent property. So then we want to take the dimensional change into consideration. Then we have the shear stress component. So in this constitutive model, the octahedral shear stress term is added to this model. And then, however, this one is the stress-dependent simulation model. In this model, especially when we use the commercial simulation software such as Abacus to do the calculation, we will waste a lot of time and need more calculation capacity. And then we change the stress-dependent model to the strain-dependent model. So it will be more convenient for computation. And then in this model, strain-dependent model, we use the fixed point iteration. So here are the simulation work results. So here I give you the comparison between the inverted pavement and the conventional pavement. We are using both the nonlinear model and also the linear model. Here are the comparison of the strain in X direction. And we also did comparison of the deflection in both the 2 different pavement structures. And then we can have the output of the stiffness distribution within the unbound aggregate base. As you can see, the figure A is the inverted pavement, the figure B is the conventional pavement. So in the unbound aggregate base of the inverted pavement base, you can say as the distance from the loading point or loading area, the stiffness, the modulus or the stiffness of the unbound aggregate base will decrease a lot. However, in the conventional pavements, you can say in the unbound aggregate base, the stiffness didn't change a lot. So we have the highlights for the preliminary numerical simulations. The first is that nonlinear stress-dependent characteristic of the unbound aggregate base layer has a larger influence on the structural response of the inverted pavement. but little effect could be found in the conventional pavement. The second one is stress history makes the stiffness of the unbound aggregate base layer changeable, and this phenomenon is more obvious in the inverted pavement. And the last one is the inverted pavement has different structural responses, such as the stress, strain, and the deflection, compared to the conventional flexible pavement structure in Hong Kong. So after the preliminary numerical simulations, we have to do some tests to do some field investigation of the inverted pavement. So we found the in-service inverted pavement in the states in Knoxville, Tennessee of the United States of America. So firstly, we conducted the non-destructive tests such as GPR ground penetration radar, Pavement beam test, 3D road profiling test, and also the falling weight deflectometer. So first of all, we conducted the GPR test to validate the pavement layer thickness. Things due to the construction quality, sometimes we give you a design, but design of the pavement structures, but the construction quality is not guaranteed. So there are some difference between the design thickness and the construction thickness. So based on the GPR results, we found that the difference between the average measured and designed thickness was less than 5 millimeters in the inverted pavement. So it shows that the construction quality is very good. So then we conducted the very classic Pavement beam test. So here are the figures to show the overview of the Pavement beam test. So for the Pavement beam test, so usually an 80 kilonewton test load on single rear axle, the beam was placed between the tails so that the probe is 1.37 meter forward to the rear axle. So we have the results. So the first one is no deflection was detected by the BBT in the inverted section. And the number two result is the average deflection of 0.326 millimeter was reported in the conventional section. It means that the inverted pavement has a better condition compared to the conventional section. And then we conducted the 3D road profiling test. We measure the cracking length and both in the longitudinal direction and the transverse direction. And we'll also measure the IRI, the International Roughness Index, and the rotting depth. So based on the results, we found that the inverted pavement section outperformed the conventional pavement section in red quality, cracking, and rotting as well. So then we conducted the FWD test, the falling weight deflectometer test. Here is the picture to show the overview of the FWD experimental framework. So we did this test on both the conventional section and also the inverted section. So here are the law behind the test. So here the FWD test will give a FWD load, and then there is a distance from the load point. So then we for the FWD load, it's amplitude pattern of the impulse load in the FWD test. So here I give you a short video to show the how the falling weight deflectometer motion test on the pavement surface. Okay. So then for the Vulkan inverted pavement, we also conducted the cost analysis. So we used the EUAC, the estimated uniform annual cost, to calculate and compare which payment structure is more cost efficient. So we give all the cost analysis of the testing payments. Then we can calculate the total cost USD per lane mile. So then we got the results for the inverted payments. The EUAC value is 22,000 something, and for the conventional payment structure is the 34,000 something. So then we can conclude that the inverted payment is more cost efficient based on the data from the in-service Vulkan inverted payment. So just now I introduced the FW test. So based on the FW test, we can get the data from the test to draw the deflection basin curve. So based on the deflection basin parameters, so here we can get the D0, D300, D600, and D900 to calculate the surface SCI value, BDI value, BCI value. So here I gave you the meaning of the different names, such as SCI is the surface layer condition to can clarify the surface layer condition. The BDI can tell you the intermediate layer condition, and BCI can tell you the lower layer condition. So we, based on the data from the Vulkan inverted payments, we got the SCI value, the BDI value, and also the BCI value. So here we, based on the SCI comparison, we found that the same pulse load induced more deflection on a thinner asphalt layer. And for the BDI value, we can find that the unbound aggregate base layer dispersed the stress and mitigated the stress dissipation from top to bottom, and due to the denser unbound aggregate base. And for the BCI value, we found that the SG subgrid of the inverted pavement benefited from the UAB layer and also the inverted structure. So then we used the nonlinear simulation work to do the numerical simulation. And the error percentage is within 15%. And then we can make a comparison study between the finite element simulation and the field data in the inverted and conventional pavement sections. And here are the, for the figure 13, it is the calculated deflection of the subgrade surface in the inverted and conventional pavement. We can see that the deformation of the subgrade layer surface of the inverted section is smaller than that of the conventional section. It means that the inverted pavement has a better performance. And figure 14 give us did the comparison of the horizontal stress distribution between the inverted and conventional pavements. As you can see that at the bottom of the asphalt concrete layer, the tensile stress of the inverted pavement is much smaller than that of the conventional pavement. So as you know that the smaller tensile stress at the bottom of the asphalt layer means that it will be much more safer, and larger tensile stress will result in the cracking of the bottom of the asphalt layer. So both the two figures show that the inverted pavements outperformed the conventional pavement structures in the deflection and also the stress distribution. And then based on the simulation work of the FWD data in the volcano inverted pavement, we also found that in the inverted pavement, in the ambient aggregate base, there is very obvious stress-dependent phenomenon. But in the conventional pavement, the change of the stress in the ambient aggregate base is very small. So there is no obvious stress-dependent property. So we have the FWD data. Just now we also introduced the SI, BDI values to do the briefly evaluation of the pavement performance. And then we want to know how to use this method to assess the inverted pavement more comprehensively. So we changed the modulus of the asphalt concrete layer, cement treaty base layer, and also the subgrade soil layer. Due to the stress-dependent property of the ambient aggregate base, we didn't assign any different modulus to the ambient aggregate base. So here we can also have the deflection range of the asphalt concrete layer surface under the FWD laws. So firstly, we changed the modulus of the asphalt concrete layer and then changed the modulus of the cement treaty base layer. And lastly, we changed the modulus of the subgrade. We can find that when we change the modulus of the subgrades on the figure on our right, at the right, we can find that the deflection is changed the mostly. And when we change the modulus of the asphalt, the surface layer, asphalt surface layer, the deflection change is very limited. And then we compare the SCI, BDI, BCI values with the change of the different layers modulus. We can also draw the same conclusion that the modulus of the subgrade layer will contribute most to the deflection of the inverted pavement structure. And here we found the evaluation index parameters for the with the different asphalt thickness and different evaluation range and the evaluation results. And the table 4 and table 5, there are two evaluation systems. So based on the two systems, we can draw the figure 19, the change of the DBPs along the testing inverted pavement section. We can find that the inverted pavement after 2 years service, the volcano inverted pavement also all layers are in very good condition. And the fourth chapter, we did the full-scale APD test, is the accelerated pavement testing. So this test is also in the States, University of Tennessee. Here I give you the dimension, the length, the weight, and height. The running speed of the dual wheel system was set at 3.6 per pass, and it's around 1,000 passes per hour. And a lot of 80 kilonewtons was applied, and the contact pressure between the wheel and pavement surface was 1.4 megapascal. And here is a short video to show you how this machine tests. Okay. So then we have a pavement pit. So we divided this pit into three lengths. The middle one is for the benchmark for comparison, and the lane on the left and on the right is the inverted pavement with the different thicknesses of the unbound aggregate base and cemented base. So then after we finish the test, we draw the surface deflection contour map. So as you can see, the figure B is the conventional pavement. The deflection has the largest value compared to the inverted pavement lane on the left and on the right. And also draw the pavement profile based on the surface deflection. The figure B is also the figure B is also the conventional pavement lane. So as you can see, the figure B has passed the failure criterion value, and the inverted pavement on the right, the figure C, has a smallest deflection value. So then the last chapter is to how we can reinforce the inverted pavement further. So we consider the geosynthetics, geogrids. So we conducted the second round test. We also use the same pit, but we inverted the geogrids layer within the unbound aggregate base at different locations. One is at the up 1/3 layer, and one is at the lower 1/3 layer. And table 7 gives you the properties of the geogrid, the aperture size, the tensile strength, the tensile stiffness, and junction efficiency. And here I showed all the procedures to construct the pavements, and also how to insert the geogrids. Firstly, we have to compact the subgrids. And when we finish the compaction, we have to place the cemented base. We have to mix the 4% cement with the aggregates and spray some water. And after 7-day curing, we have to place the aggregate unbound aggregate base layer, and we have to insert the pre-stressed geogrid within the unbound aggregate base and the compaction, and then we place the asphalt surface layer. And here I marked a lot of points on the pavement surface to do the deflection testing. And the figure A, you can see it's for the APT, it is a bidirectional loading process. And the figure B is the testing points of the surface deformation. So after the testing, we found that the pavement 3, the inverted pavement within the geogrid has the smallest deflection value. It means that the geogrid can contribute to the structural performance of the inverted pavement compared to the pavement 2 of the conventional flexible pavement. And then we'll also draw the deflection contour map of the pavement surface. And we found that the lower 2/3 location degrades the rotting performance, and the upper 1/3 location improved the rotting resistance. So why for the first result, the lower 2/3 location degrades the rotting performance? After the test, we found that this result is due to the improperly placement of the geogrids. So then, based on the testing value or data. We have the evaluation indexes such as triple R, TBR, and ROD. The first one is the rotting reduction ratio, traffic benefit ratio, rate of the deformation. So the triple R represents the ratio of the rotting depth of the reinforced inverted pavement to that of the unreinforced inverted pavement lane at the same number of lot circles. Here we set the 150K as the number. And the TBR is defined as the ratio of the required number of lot cycles to reach a certain rotting depth in the reinforced inverted pavement lane to the required number of the lot cycles to meet the same rotting depth. Here we set the 9 millimeter as the standard value in the unreinforced inverted pavement lane. And the ROD, rate of the deformation, is defined as the development rate of the permanent surface deformation. Here we set the value as the 9 millimeters. And then we form that we get the calculation results and draw this table. And we found that the pavement length number 3, the inverted pavement, has the best performance. And then we also cooperate the testing data with the simulation work to validate the stress-dependent property of the unbound aggregate base layer in the inverted pavement. The figure A is the stiffness distribution, and the figure B is the strain distribution. At the beginning of the presentation, I introduced that we developed a new constitutive model from the stress-dependent to strain-dependent. So here, we also focus on the strain distribution within the unbound aggregate base. And then we draw this figure to show that within the unbound aggregate base layer, the stress will decrease with the distance from the loading points or loading areas. And here are the pavements trench cuts to show that the deflection or the permanent deformation of each layer of the pavement structures. And finally, and this research is still going on. So many data we have not finished analyzing. So based on all the data we have finished the analyzing, we can draw the following conclusions. The first one is the nonlinear stress-dependent characteristic of the unbound aggregate base layer has a large influence on the structural response of the inverted pavement, but little effect could be found in the conventional pavement. The second one is that the stress history makes the stiffness of the unbound aggregate base layer changeable, and this phenomenon is more obvious in the inverted pavement. And the third one is that based on the overall performance, both the field and the testing data, the inverted pavement can be regarded as a good alternative to the conventional or the traditional flexible pavement. And the last one is the geogrids could improve the rotting resistance of the inverted pavement, but the installment location is of great importance. So thank you, everyone. That's my presentation.
Thank you very much, Dr. Jiang. So if you have any question, please feel free to type your question in the Q&A box now.
Yeah. Okay.
Yeah, it seems there's no question from the floor.
Yeah, there is one I see from our chatting box, Q&A box. Is there any specific code for this payment? Okay, so that's a good question. So now because this payment structure actually originated from the South Africa, because South Africa want to save more materials. They want to reduce the utilization of the asphalt materials, and so they use the cement treated base layer. But so far, in the South Africa and also in the United States of America, there is no specific standard for this payment design. So now this payment structure is still open to do research. Yeah. So I remember that we have a project from the U.S. Federal Highway Administration, FHWA. That project is, I think, is given to the UIUC, University of Illinois Champaign, and Professor Tutumuna conducted this project to. Now they are doing the kind of a literature review and collecting all the practical experience and data about the inverted pavement. Yeah. So the second question, would the additional layers introduce difficulties to trench excavation for underground utilities? Okay, that's also a good question. So actually, this because we have 4 layers for the inverted pavement. So above the at the bottom we have the compaction subgrade soil layer. So above this one we will place the cement treated base layer, and the cement percentage is just a 4%. So for this layer, the compressive strength is only 2 or 3 megapascals. So I think there is no difficulty for to trench excavation. Yeah. So the next one from very low, where the result be different if the soft ground underneath. Okay, I think that's a very good question. So for the soft ground formation, so usually because we have the very specific standard for the compaction quality of the subgrade soil layer. So if the subgrade contains too much water, we will when we when we see the subgrade soil layer, we will dry it out, and then we compact the subgrade soil to meet the quality requirements of the standard, and then we can build up the pavement layers. Yeah, I think the results will be the same. Yeah, because the subgrade must meet the requirements of the compaction. Did you, okay. How much improvement in terms of durability of the inverted pavement compared with traditional flexible pavement? Okay, it's a very good question. So, so far, we have very limited practical construction. So in the state of Tennessee, we found the in-service inverted pavement, which is the driveway for the quarry. So the traffic load is a lot. So after 3 years service, the inverted pavement, I just show the results because we conducted the 3D pavement profiling test based on the results of the IRI roughness and also the cracking and also the deformation. The inverted pavement outperformed the conventional one. Yeah. Okay. The second and the next one is: did you investigate repairing pit holes in conventional pavement with the invert? Oh, that's a good point. So far, we didn't conduct such a research, but in our in the future research, I think is a very interesting point. Okay, the last one, where the increase in the production cost exceed the benefits brought by the inverted pavement. Okay, that's a very good question. Okay, so actually, at the beginning of the presentation, I did a comparison study between the inverted pavement and the conventional pavement. Actually, the thickness of the asphalt layer of the inverted pavement is just 1/3 of the thickness of the conventional pavement. So maybe you will think that we have to make the cement treated base layer to mix the cement with aggregate, but this cost for the cement treated base layer is much less than the cost of the asphalt materials. So just now I also showed the cost analysis in the in my slides. And the results show that the inverted pavement, based on the structural performance, the inverted pavement has better cost efficiency compared to the conventional flexible pavement. Yeah. But there is a limitation for my calculation, is that because the in-service inverted pavement is just finish its 3 years service. So we have to continue to do the FW test and also the 3D profiling test to track and monitor the pavement condition after longer years service. Yeah. So at least I think within 5 years, the inverted pavement will be better than the conventional. But after 10 years or 20 years, that's a very big concern. Yeah. Wow, the cost is lower than, that's cool. Thank you. Thank you. Yeah. The title of the talk, Sustainable Decarbonizing, did you compare embodied carbon? Yes, that's a very good question. So for the sustainable or decarbonizing, here I didn't add several slides because our presentation is 40 minutes. So actually, for the inverted pavement, things we use less asphalt materials. As you all know, that the asphalt is made from the crude oil. So we cut the usage of the asphalt, and then it will means that we cut the usage, we cut the embodied carbon, we cut the carbon emission. Island difference for the reinstatement will compare with the traditional methods. Yeah, that's a good question. For the okay, So for the construction of the two pavement structures, I think the difference there's a difference between the two structural construction is that the pavement is I think is mainly on the unbound aggregate base layer. So in the inverted pavement, we want to strengthen its the aggregate interlocking. So we will remove some very fine aggregates when we build the unbound aggregate base layer for the inverted pavement. So that's the difference. Yeah. And for the asphalt layer, it's the same. For the subgrade soil layer, it's the same. Yeah. And for the cement treated base layer, it's just for inverted pavement, and no cement treated base in the conventional one. Yeah. Okay. Yeah. PPT, please. Okay. After today's presentation, I will give you a more brief slides. Okay. Since we some results are still working out, so I cannot give you all the slides, but I can give you a simple one. Yeah.
Okay, thank you, Dr. Jiang. I think there are no more questions from the floor. Yeah, so yeah, thank you again for Dr. Jiang for your insightful presentation. I hope you all enjoy the presentation tonight.
Yeah.
So thank you all, and this is the end of this seminar. Thank you, and
Okay.
goodbye.
Thank you, Harry.
Thank you.
Bye-bye.
Bye-bye.